The objective of this project was to communicate the process of design while designing a wing given the following constraints. The main idea was to optimise for minimum mass while still adhering to the brief. This process could be split up into 4 main stages. The first stage of every design process is conceptual design, involving initial sketches of the design and assumptions about its performance. In this stage, we use pen and paper to draw simple sketches of the primary structure of the wing, the spar, as well as the secondary structures consisting of the leading edge, the trailing edge, and the ribs. We also sketch the bending moment and deflection diagrams to estimate how the spar will perform, assuming the mass of the aircraft is concentrated at the fuselage and supported by point loads at the wingtips, effectively a cantilever beam. Therefore, the maximum bending moment will be at the root and decrease to 0 at the tip. The deflection, however, will be maximum at the tip and 0 at the root.
The main tool we used throughout the preliminary design was the distributed Excel sheet. In order to use Excel, we made some assumptions. It allowed us to see the consequences of tweaking our design in real time, while incorporating standard material properties for the foam board used. GeoGebra was also used to determine the optimal design, graphing the mass and maximum stress, and taking the point of minimum mass while maximum stress experienced by the spar was just under the ultimate strength of the foam board material.
Excel is a very useful tool to provide quick ideas while constructing and making sure we're going in the right direction. Using beam theory, it allowed us to calculate bending moment, torsion and stresses in the bar for different input values very easily, and it also allowed us to confirm the design fits within the rib. Since the spar would experience both bending and torsion, the second moment of area and polar moment of area would play key parts. As these share an inverse relationship, Excel was used to find dimensions that featured a balance of both.
For the detailed design, we implemented the parameters we found in Excel into SolidWorks. This allowed us to gain more accurate data as SolidWorks isn't limited by the same assumptions in Excel. The spar was given most of the attention when simulating for simplicity, as it was the main load carrying part. In the lab, we did bending and torsion experiments to find the material properties of the foam board. This included the elastic modulus, the shear modulus, and ultimate stress. These could then be inputted into CAD to output a detailed and accurate 3-dimensional simulation of our spar. You can see that most of the stresses are concentrated at the root, whereas the tip isn't taking a lot of stress. SolidWorks is an amazing tool which allows us to experiment with the dimensions in new ways. This included tapering the tip or adding holes to the sides. Both of these methods reduce the weight of the wing by removing areas of the beam not being used efficiently enough. However, tapering is the better method as it reduces more weight while still keeping the material properties intact. Unfortunately, a common sacrifice that comes with increased efficiency is a reduction in ease of manufacture. A tapered spar is very difficult to make, especially out of foam board, and so we kept it simple with a uniform rectangular cross section. Still, in real life, the spar won't perform exactly as SolidWorks says it will. This is due to other factors such as manufacturing or measurement errors, as well as the material properties potentially not being as we measured. This brings us back to the design process, where we would start again with our newfound knowledge to further create a much better and optimised wing design, and so the process reiterates, each time getting closer to perfection.